Hello, in today's video, I'll be solving questions on metals under IGCSE Chemistry. A lot of the questions I'm going to be solving today are centered around reactivity series of metals and extraction of iron. So I want to do a brief explanation of the reactivity series and extraction of metals before we delve into solving of the questions. This is the commonest reactivity series used in IGCSE Chemistry. The metals have been arranged from the most reactive metal on top to the least reactive metal at the bottom. This reactivity series was deduced by reacting the metals with cold water, steam, dilute acid, and oxygen, and observing the reactions that take place. Based on the reaction, they can tell that one metal is more reactive than another. The most reactive metals on top can react with cold water. So from potassium, which is the most reactive because potassium can easily lose electrons than all the other metals in the reactivity series. So that is why potassium is the most reactive. So these three metals can react with cold water. So by cold water, you mean H2O liquid. Then from magnesium and aluminium to some extent will react with steam. So these ones can react with H2O gas. The metals between carbon and hydrogen cannot react with steam or will not readily react with steam. So we use dilute acid. So they can react with dilute acid and oxygen. In fact, these ones readily react with oxygen. And all the metals from iron all the way to the top can react with dilute acid. For group 1 metals, it is very dangerous or risky to react them with dilute acid because already when you react them with normal water, cold water, the reaction is very vigorous, exothermic, and could even pose dangers. How much more reacting with an acid? All the metals below hydrogen are very unreactive, or they are least reactive of all the metals. So they do not react with cold water, steam, oxygen, or dilute acids. But copper can react with oxygen among these three. The rest do not react at all. Carbon and hydrogen are non-metals, but they are found in the metal reactivity series because they are used as references to know which extraction method to use for a particular metal. In the extraction of metals from their metal ores, all metals that fall above or are on top of carbon are more reactive than carbon. So we can't use carbon to reduce their ores in order to get the metal. So we have to use electrolysis to extract these metals from their ores. All metals that fall below carbon, so from zinc all the way to say copper, or silver are less reactive than carbon. And so for that matter, carbon can be used to reduce their ore. Metals like gold and platinum are found and combined in the earth crust. So they are not combined with any other element. They exist as the pure forms of these metals. Like gold, you find gold from the earth crust uncombined. You also find platinum from the earth crust uncombined. So these metals are called native metals. Based on these two extraction methods, iron falls below carbon. It means that iron is less reactive than carbon, and so we can use carbon to reduce the iron ore in order to get iron. Talking about aluminium, aluminium is on top of carbon, so if you want to get aluminium from aluminium ore, you have to use electrolysis. So let's talk briefly about the extraction of iron using carbon to reduce the iron ore. The ore of iron is called hematite. Hematite is mainly made up of iron 3 oxide, which is Fe2O3, and an impurity called silicon 4 oxide, which is SiO2. SiO2 is also called silicon dioxide. The process is carried out in a chamber called blast furnace. And in this chamber, the hematite is reduced using carbon. This is a diagram of a blast furnace. The raw materials used in the extraction of iron are fed through the top of the blast furnace. There are three raw materials fed into the blast furnace. The first is the hematite, and we said the hematite mainly contains iron 3 oxide and silicon dioxide impurity. So you have hematite limestone. Limestone is the same as calcium carbonate, and that is CaCO3. And also coke. Coke is an impure form of carbon. There are two main processes in the extraction of iron. The first one is the removal of the impurity from the hematite, which is silicon dioxide. And the second is the removal of iron from the iron 3 oxide. To remove the impurity, the calcium carbonate raw material, which is limestone, fed into the blast furnace, first undergoes thermal decomposition to produce calcium oxide plus carbon dioxide. The calcium oxide produced from this thermal decomposition is a basic oxide, and the impurity, silicon dioxide, is an acidic oxide. So the calcium oxide reacts with the silicon dioxide through a neutralization reaction to produce calcium silicate, CaSiO3. This calcium silicate, and the common name of the calcium silicate is what we call slag. And this slag is less dense than the iron, the molten iron. So it flows to the bottom of the blast furnace through this opening, and then it is tapped off from the chamber. The iron ore is then taken through the second stage, where iron inside the iron 3 oxide is then removed, and then the molten iron flows to the bottom since it is heavier than the slag. So let's look at the second stage that leads us to the removal of the iron. To remove iron from iron 3 oxide, we need a reducing agent, so we add coke, which is the impure form of carbon. But coke is not actually a strong reducing agent, so the coke actually helps us to produce a strong reducing agent. The first reaction that takes place is the coke reacting with oxygen, or what we call hot air, which is directed through the opening, this opening at the bottom of the blast furnace. And once the hot air, which is oxygen, reacts with the coke, it produces carbon dioxide. The carbon dioxide now reacts with more coke, or it is reduced to produce carbon monoxide. And carbon monoxide is a stronger reducing agent than carbon. So the carbon monoxide now reacts with the iron 3 oxide and reduces this carbon monoxide and reduces the iron 3 oxide to iron, and then in turn is oxidized to carbon dioxide. So carbon monoxide is the reducing agent. It reduces iron 3 oxide to iron, and a reducing agent, once it is done reducing another substance, it will itself undergo oxidation. And so to balance this, we just have to put 3 here because we want to make oxygen on the reactant side even. So using 3 will make it 6. And once oxygen is 6 at the reactant side, we can just put 3 here, and that will make oxygen also 6 at the product side. And iron is 2 at the reactant side, so we just have to put 2 at the product side. And this balances this equation. The iron produced now moves to this part, or through this opening A, and it is also tapped off. The carbon dioxide produced in this reaction is a waste gas, so it is going to come out through this opening. There are two more waste gases like nitrogen and argon, because nitrogen is already in air. So once this reaction is taking place, nitrogen also finds its way into this chamber, and so it has to come out. Argon is also in air, so it has to come out of the chamber. Now we can solve the questions. The first question is from Feb-Mar 2024, paper 4.2. Question 1. Iron ore contains iron 3 oxide, Fe2O3. A blast furnace is used to extract iron from iron 3 oxide. Equations for some of the reactions in the blast furnace are shown. Equation 1. Carbon plus O2 giving carbon dioxide. Equation 2. Calcium carbonate decomposes to give calcium oxide plus CO2. Equation 3. Calcium oxide reacts with silicon dioxide to give calcium silicate. A. Equation 1 shows the combustion of carbon in the blast furnace. I. Name the substance which provides the carbon for this reaction. So we said coke is the impure form of carbon, and so it is coke that is used to give us the carbon. II. State the purpose of the combustion of coke in the blast furnace. Coke is actually a black solid like charcoal that is burnt to provide heat for the chamber. B. Iron 3 oxide Fe2O3 in iron ore is converted to iron when it reacts with carbon monoxide CO in the blast furnace. I. Calculate the percentage by mass of iron in iron 3 oxide Fe2O3. So to calculate percentage of iron, it is equal to the molar mass of iron divided by the molar mass of the whole compound in which iron is found. So iron 3 oxide times 100. Now the molar mass of the atomic mass of iron from the periodic table is 56, and there are 2 iron atoms in this compound. So that is going to be 2 times 56 divided by the molar mass of this compound. There are 2 atoms of iron in this compound, so 2 times 56 plus the atomic mass of oxygen is 16. So that's 16 times 3, all times 100. If you do this, you get 70% of iron in iron 3 oxide. II. State the name of the ore, of the iron ore, which consists mainly iron 3 oxide. So we said this is hematite. Hematite is the ore of iron. III. Describe how carbon monoxide is formed in the blast furnace. So when we looked at the reactions, we saw that when carbon dioxide, that's CO2, is reduced with coke, that is carbon, then we tend to produce carbon monoxide. So that reaction was CO2 plus C, giving us 2 moles of carbon monoxide. So we reduce carbon dioxide with coke to produce carbon monoxide. IV. Write the symbol equation to show the reaction that occurs when iron 3 oxide is converted to iron in the blast furnace. So we saw from the reactions that we talked about earlier that the iron 3 oxide reacts with a stronger reducing agent, which is carbon monoxide, to produce iron. So in this case, the iron 3 oxide has been reduced to iron, plus the reducing agent, which is carbon monoxide, after reducing the iron 3 oxide, will now undergo oxidation. So it's going to gain oxygen to give carbon dioxide. To balance this, we place 3 here, 3 here, and 2 at this side. V. Name the chemical process which happens to iron when iron 3 oxide is converted to iron in the blast furnace. So iron 3 oxide here is converted to iron, and that is actually reduction, because to get the iron 3 oxide had to lose oxygen. and so the process is reduction. C. State the type of reaction shown by equation 2. This is equation 2. Equation 2 is actually thermal decomposition of calcium carbonate, because calcium carbonate or limestone was broken down using heat to produce calcium oxide and carbon dioxide. D. I. Explain why the reaction in equation 3 can be described as an acid-base reaction. So equation 3 is the reaction between calcium oxide and silicon dioxide. Calcium oxide is a basic oxide, and silicon dioxide, SiO2, is an acidic oxide. And anytime a base and an acid react, we call it a neutralization reaction. II. State the chemical name of SiO2. That is silicon 4 IV oxide. The 4 is the oxidation number of silicon. So if you want to find the oxidation number of silicon here, that will be Si plus. The oxidation number of oxygen in most of its compounds is -2, but there are 2 atoms of oxygen there, so times 2, and this is equal to the charge on the SiO2, 0. So silicon minus 4 is equal to 0. So we can see that what silicon is equal to plus 4. So that's why it's silicon 4 oxide. State the common name given to CaSiO3, calcium silicate, when it is formed in the blast furnace. So the common name for calcium silicate is slag. E. Aluminium cannot be extracted from its ore using a blast furnace. I. States why aluminium is not extracted from its ore using a blast furnace. So we only use the blast furnace when the metal is below carbon in the reactivity series, which means carbon is more reactive than that metal, and so carbon can be used to reduce the ore of that metal in order to get the metal. But when you check the reactivity series, we saw that aluminium is above carbon in the reactivity series, and so we need to use electrolysis. So for this question, we need to say that aluminium is more reactive than carbon. II. Name the process used to extract aluminium from its ore. So we saw this to be electrolysis. The next question is question 6 of May-June 2024, paper 4-1. Question 6. This question is about metals. A. Figure 6.1 shows a blast furnace used to extract iron from its ore. So this is figure 6.1. I. Coke and iron ore are added to the top of the blast furnace. So on top here, we have coke and iron ore entering the blast furnace. Name one other substance that is added to the top of the blast furnace. Aside coke and iron ore is same as hematite. Limestone is also added to the blast furnace. So limestone is also called calcium carbonate. II. Name the substance that leaves the blast furnace at A. So we said slag is on top here, molten iron is beneath the slag, because iron is more dense than slag. So iron has to flow to the bottom part of the blast furnace. It is molten iron because the iron has been melted into the liquid state, because the temperature of the blast furnace is at the melting point of the iron. So the iron has been melted. III. Slag is produced from an impurity in iron ore. Name the impurity in iron ore that is converted into slag. So this is silicon 4 oxide. Silicon 4 oxide is also the same as silicon dioxide. IV. Name 2 substances that react together to produce the high temperature in the blast furnace. So we said coke was burnt to produce heat for the chamber, and actually coke burns in the presence of oxygen. V. Name two waste gases that leave the blast furnace. So carbon dioxide is one of the waste gases that leaves the blast furnace during the extraction of iron. Nitrogen gas is also one, and argon is also another one. B. Zinc is produced from zinc oxide in a furnace. The zinc is produced as a gas. It then forms molten zinc. I. Suggests why the zinc produced inside the furnace is a gas. So zinc is a metal, but for zinc to be a gas, then it means that zinc has reached its boiling point. And so for that to happen, it means that the temperature of the furnace is above the boiling point of zinc. And so it is the reason why the zinc has been vaporized into the gaseous state. II. State the name of the physical change that occurs when gaseous zinc is converted into molten zinc. So for a gas to be converted into a liquid, molten means liquid zinc. That process is called condensation. C. Zinc is used to coat iron to prevent rusting. I. Name the process used to coat iron with zinc as a method of rust prevention. So when you put zinc on the surface of iron, that is a sacrificial protection. But the specific type of sacrificial protection is what we call galvanization. So galvanization is a relationship between iron and zinc, where iron is coated on the surface of, zinc is coated on the surface of iron in order to protect the iron through sacrificial protection. II. When the zinc coating is crushed, the iron underneath does not rust. Explain why the iron underneath the zinc does not rust. Once the zinc on the surface of the iron is crushed, the inner layer of the zinc is exposed to air and water. And so the zinc being more reactive than iron, it is going to undergo oxidation in order to protect the iron from rusting. So you have to say that zinc is more reactive than iron, so it is oxidized first, or in other words, it corrodes first. And once it corrodes, it protects the iron which is beneath it from rusting. So in order to continue protecting the iron from rusting, the zinc coating must be replaced regularly. D. Zinc oxide neutralizes both acids and bases. I. State the general name given to oxides that neutralize both acids and bases. Any oxide that neutralizes an acid or a base, we call it amphoteric oxide. An example is aluminium oxide and zinc 2 oxide. II. When zinc oxide neutralizes aqueous sodium hydroxide, sodium zincate is formed. The formula of the zincate ion is ZnO2 2-. Deduce the formula of sodium zincate. So sodium ion and the zincate ion reacting together, the 2 goes to the bottom of sodium and the plus goes to the other side. It means that we are getting Na2 into bracket ZnO2 1. But anytime you multiply a value or a letter by 1, you still get the same letter. So for that matter, the formula of sodium zincate is going to be Na2ZnO2. III. Name the zinc compound that forms when zinc oxide neutralizes dilute sulfuric acid. Zinc oxide is amphoteric, and so this time, as it is reacting with sulfuric acid, it is now acting as a base. And once a base and an acid reacts, we get a salt plus water. So the zinc compound formed here is zinc 2 sulfate, or sometimes they just call it zinc sulfate. The next question is question 2 of May June 2024, paper 4-2. Question 2, a list of 5 metals is shown: copper, iron, magnesium, potassium, and silver. A. All metals form positive ions. I. Describe how atoms form positive ions. For an atom to form a positive ion, it must lose electrons. So they do so by losing electrons. II. State which of the 5 metals in the list has the greatest tendency to form positive ions. We know that metals lose electrons to form positive ions. The ability of a metal to lose electrons makes that metal more reactive. And when we look at the reactivity series, we can see that potassium is the most reactive because it has the ability to lose electrons more readily. So from the list, potassium is the metal that has the ability, or the greatest ability, to readily lose electrons. III. Suggest one of the 5 metals in the list which is not likely to show catalytic properties. It is transition metals that show catalytic properties, and so potassium and magnesium are not transition metals in this list. So this has to be either magnesium or potassium. IV. State which of the 5 metals in the list is a major component of stainless steel. So to form or to produce stainless steel, iron is used. And from the list, we can see iron in the list. And iron is the major component in stainless steel. B. A student asks a sample of a metal to an aqueous metal salt in a beaker to see if a displacement reaction takes place. Complete table 2.1 to show the color of the solution in the beaker at the start and at the end of the experiment. In the displacement reactions of a metal and metal salt solutions, if the metal is more reactive than the metal ion in the salt, then it means that the metal is going to displace the metal ion in the salt. And the reactivity series can also help us know which metal is more reactive or not. For magnesium and iron, if you look at the reactivity series, we can see that magnesium is on top of iron. That makes magnesium more reactive than iron. So magnesium is going to displace iron 2 from the iron 2 sulfate salt to produce magnesium sulfate and iron metal. Magnesium sulfate is a colorless solution because the magnesium is not a transition metal. It is transition metal salt solutions that give colors. The next one, so for silver and copper, from the reactivity series, we can see that copper is on top of silver. It means that copper is more reactive than silver. So there is no way silver can displace copper from this salt. And so for copper 2 solutions, we see a blue color. And since silver cannot displace copper in this salt solution, it means that we are going to get a blue color at the end of the reaction. In fact, no reaction takes place, so the solution is going to stay the same as a blue solution. C. Most group 2 metals form a gas when placed into cold water. An alkaline solution is also formed. I. Name the gas formed when strontium is added to cold water. Metals that react with cold water produces metal hydroxide solutions and hydrogen gas. So it means that the gas produced over here is hydrogen gas. II. Name the alkaline solution formed when strontium is added to water. So the strontium hydroxide produced here is the alkaline solution. So we have to write the name and not the chemical formula. III. One group 2 metal reacts very slowly when placed in cold water. When heated, the metal reacts with steam to form a white solid. Identify this metal and name the white solid formed. So let's look at the reactivity series again. We said from potassium to calcium, these metals react with cold water. And from magnesium to aluminum, they react with steam. And since we are talking about group 2 metals, magnesium is the only group 2 metal that reacts with steam. So this metal has to be magnesium. And for the white solid form, when magnesium reacts with steam, any metal that reacts with steam, notice that we are using H2O gas and not H2O liquid, produces a metal oxide and hydrogen gas. So it means that the white solid has to be magnesium oxide. We are supposed to name and not write the chemical formula. D. Under certain conditions, iron will react with steam to form an oxide of iron with the formula Fe3O4. Fe3O4 reacts with dilute hydrochloric acid to form a mixture of iron 2 and iron 3 salt and water. Deduce the symbol equation for the reaction between Fe3O4 and dilute hydrochloric acid. So we have Fe3O4 plus dilute hydrochloric acid HCl, giving us now this Fe3O4 is a basic oxide and HCl is an acid. So anytime a base and an acid react, we get salt and water. And from the question, we're told that we are getting iron 2 salt and iron 3 salt. So it means that these two salts have to be iron 2 chloride, that is FeCl2, plus iron 3 chloride, that is FeCl3, then plus H2O. To balance this equation, oxygen is 4 at the reactant side, but 1 at the product side. So we have to put 4 here. The moment we put 4 here, hydrogen is 8 at the product side, but 1 at the reactant side. So you have to put 8 at this side. And when we do that, we can see that chlorine is 8 at the product side, but chlorine is just 2 plus 3, that is 5 on the product side. So to balance chlorine at the product side, you have to put 2 here, and that will make 6 chlorines plus 2 chlorines, and that gives us 8 chlorines at the product side, which is equal to the number of chlorines at the reactant side. Then iron is also 3 atoms of iron here, and this is 1 plus 2 atoms, and that gives us 3 atoms of iron on either side of the equation. The last question is question 6 of May-June 2024, paper 4-3. Question 6. This question is about iron. A. Figure 6.1 shows a blast furnace used to extract iron from its ore. I. Name the main ore of iron used in the blast furnace. So the ore of iron is hematite. II. Name the substance that enters the blast furnace at A. So that is hot air. The hot air is actually oxygen. It is this oxygen that is blown into the chamber that reacts with coke to provide heat for the chamber. III. Name the reducing agents in the extraction of iron in the blast furnace. So the reducing agents used is carbon monoxide. It is not coke or carbon, because coke is not a stronger reducing agent. So the coke has been converted into carbon monoxide, which is a stronger reducing agent to reduce the iron 3 oxide to get the iron. IV. Explain why limestone is added to the blast furnace. Give details of the chemical reactions that are involved. So when limestone is added to the blast furnace, it first undergoes thermal decomposition to produce calcium oxide and carbon dioxide according to this equation. The calcium oxide produced, which is a basic oxide, now react with silicon dioxide, which is the acidic impurity in the hematite, to produce slag. So the calcium oxide then help us to remove the impurity in the form of calcium silicate, which is slag. B. The list shows the properties of some elements. First one, act as catalysts, have low densities, have low melting points, form acidic or basic oxides, form colored compounds, form positive or negative ions. Iron is a transition metal. Sodium is a group 1 metal. State which property from the list I is true for sodium but not iron. Group 1 metals have low melting points or they have low densities compared to transition metals. II is true for iron but not sodium. Iron is a transition metal and so it can be used as a catalyst. Iron can also form colored compounds, but group 1 metals, including sodium, cannot be used as catalysts or cannot form colored compounds. III is true for both sodium and iron. All metals form positive ions, and so sodium and iron can also form positive ions. Sodium and iron can also form basic oxides. IV is not true for sodium and not true for iron. Form negative ions cannot be true for sodium and iron because metals form positive ions. Then metals also form basic oxides or some form amphoteric oxides. So it is non-metals that form acidic oxides. So these two metals cannot form acidic oxides. C. Steel consists mainly of iron. Iron rusts when it reacts with water and oxygen. Figure 6.1 shows magnesium blocks attached to the bottom of a steel boat. The magnesium does not completely cover the steel. The magnesium blocks provide sacrificial protection for the steel. So these are the magnesium blocks at the bottom of the steel boats. I. Explain in terms of electrons why magnesium is used for sacrificial protection. So in sacrificial protection, a more reactive metal is placed on the surface of a less reactive metal so that the more reactive metal will oxidize first. Oxidize means it will corrode first, thereby protecting the less reactive metal beneath it. Oxidation also means the loss of electrons. So it means that if the most reactive metal is the one to be oxidized first, it means that it readily loses electrons compared to the less reactive metal. So we have to say that magnesium readily loses electrons than iron, so it is more reactive than iron. And this makes it suitable to be used as a metal for sacrificial protection of iron. Note that this sacrificial protection will only work when the magnesium is scratched. But if the magnesium is not scratched and is still on the surface of the iron as how it was placed, then the magnesium now reacts with carbon dioxide and oxygen in order to produce magnesium carbonate, in which protects the iron through barrier method. II. Name a metal that cannot provide sacrificial protection for steel. So when we are talking about steel, we are referring to iron. And so for a metal to be suitable to be used as a metal for sacrificial protection of iron, it means that that metal must be more reactive than iron. So it means that the metal must be found above iron in the reactivity series. So any metal that is below iron in the reactivity series cannot be used as a metal for sacrificial protection of iron. So example of a metal that is below iron is copper, another is silver or gold. So we have to write one of them. So I'm going for copper. Thank you for watching. See you again in the next tutorial. Please subscribe to this channel.